We're going to move on. We're running a little bit pressed for time. My name is Craig Matsumoto. I'm managing editor with SDN Central, which, quick plug, we do cover SDN, yes, but we also cover software-defined pretty much anything. So we do get into cloud issues and open hardware and all that. As you heard Regine mention, our next speaker is going to be Kushagra Vaid. He is general manager of server hardware engineering at Microsoft. So his team works on all of Microsoft's cloud-sized projects, which would include Office 365 and Bing, and yes, Azure as well. His team also developed the Open Cloud Server specification, which Microsoft contributed to the Open Compute project. He's been with Microsoft since 2007, and before that was at Intel working on the Xeon platform. So he knows server stuff pretty well. And at Microsoft, by the way, he has been working on cloud and data center pretty much the whole time. He holds over 25 patents in computer architecture and data center design. So please welcome Kushagra Vaid.
Thank you. Okay, it's great to be here. Good to see a good turnout. I think there's been some really good talks this morning, and I think there's some really good talks tomorrow. So let us go through what we are doing in the cloud and what kind of innovations we're driving for cloud scale servers. So just to take a quick view of what we have in the public cloud. As most of you know, this is just an example of the kinds of applications that are out there. But you have applications that are written natively for the cloud. They're typically known as platform as a service, or PaaS, where you have APIs that are exposed by the cloud, and you write your applications to be directly running on those APIs. Then you have what's also called as infrastructure as a service, IaaS as people call it, where you bring your own workload, you put it in a VM, and the cloud is basically you run capacity. There are other applications which are already in the cloud. One example is Office 365. Some other examples are like Workday, Salesforce, which are better known as software as a service, or SaaS. So those are applications that are present essentially a service that to do a particular application function. There's a lot of people who do test development in the cloud. Cloud is used for backup and disaster recovery, and now people are trying to do batch computing in the cloud. The point here is that as the cloud is gaining more momentum and getting maturity, the kinds of workloads we are seeing in the cloud are increasing in diversity and scale. And what you will hear me say today in this talk is, as a person who has to worry about how do we design cloud infrastructure, you have to take into account everything that's on this slide and everything that will come in the future, because you want to design one common homogeneous infrastructure that can scale, that has supply chain benefits, that can accommodate a variety of flexible design points. It's cost optimized, it gives you the right performance, it's power optimized, but at the same time, it can host a variety of workloads. In the classic model for an enterprise, you would have had different design points, an HPC server, enterprise server, but in the cloud, you can't do that because of the scale. So let's take a look at the diversity of the applications in the cloud, and then how do you design a server architecture that can solve this problem in a uniform manner. Just to get a sense of scale, here's some numbers that will help you appreciate how big the scale of the cloud is. 5.8 billion queries, 8.86 trillion objects in Azure storage. It's huge, right? And the scale continues to grow. And this is not just a statement from Microsoft. Across the industry, the cloud is growing at a rapid pace. So this is a challenge that we have to address. How do you keep up with the scale, and how do you scale your infrastructure? So let's take a quick look at what does it mean to design? What does server scale mean to the design side of things? For one thing, the number of variants or SKUs, as people call it, that you can have, you want that to be extremely limited. What's shown on the slide here is 3 design points. One is for a small scale enterprise. Let's say they have 10,000 servers. The middle thing is for a hosting provider, which might be around, let's say, 100,000 servers. And then you have a cloud scale, which is more than 1 million servers in deployment, right? So you see that it's kind of an exponential scale, right? 10, 100, 1,000. And how does that change the design, right? So SKUs, you want to have as few SKUs as possible, which means that you want to have common platforms, you want to have very few configurations, how much memory you deploy, how much hard drives, what kind of CPU. You don't want to have variations there, because variations end up in supply chain complexity and support complexity. The redundancy model, it's all done by software. At this level, you can't have redundancy being done by hardware. It's too expensive, and it doesn't scale. So software redundancy, meaning doing multiple copies of data. Typically, there's 3 copies of data, either done through direct copies or erasure coding. So redundancy model is completely different for a cloud design. The availability of hardware, this might be surprising to some of you, but the hardware availability, I mean, if you look at the 2 extremes here, you go from 5 nines of availability to like maybe 2 nines, which means that it's okay if the server is designed for less than high availability. If the server goes down, that's okay. You just the software is there to load balance it. You deal with it. You move the load to a different server. The type of hardware is usually custom, because it's hard to find hardware that meets the stringent requirements from off-the-shelf designs. So you end up taking into account all the workload requirements, all the data center requirements, and custom designs. And finally, on the infrastructure design, what you have to do here is you have to take into account the broader picture for you have a server, you have a data center, you have a network, and you have the software fabric that does the load balancing and scheduling. How do you design a system that interoperates with all the other components and is optimized for the whole, not the local pieces, right? Which is something that's unique to the cloud. On the operations model, this is another place where costs can rack up pretty quickly. So you have to pay a lot of attention to what implications do you have to the design that come from operations. So the first one, is how often do you have to go service it? For break fix, hard drive fails, you have a memory DIMM that went bad. In a typical enterprise environment, you would want to go and replace it right away, because there is applications that are being held up, they can't execute. In the cloud, however, in some cases, we don't even touch that server for up to 2 weeks. The hard drive is bad, you send a guy there maybe 1 week, 2 weeks later, servers are sitting there. And the reason you can do that is because most of the scheduling is done by software, and the data is replicated in the cloud. So the operations model becomes very simple and trivial, and you save a lot of costs that way. The operations cost goes quite a bit down. For figuring out how to debug issues, when you have more than 1 million servers, you can't have a human way of debugging things. So you build tools and machine learning to auto-identify issues and go figure out what went wrong, so that by the time the human gets in the loop, it's very easy to go figure out what went wrong. System management, out-of-band management is typically very simple. Either a server is on or it's off. So you give it an on-off button basically that you can do remotely. And typically there's either a very low-end BMC, or ideally you would not even want to have a BMC. The management domain is typically thousands of servers that is managed by one entity. And when something goes bad, like I mentioned before, you don't go and replace a component. You mostly swap out the whole server, and then you go work on what needs to be replaced offline. So you can see that it's a very, very different operations model than what you would expect in an enterprise. So you take the design requirements from the previous slide, the operations requirements, and you start thinking about, okay, what does this mean? What does the server look like? So that's more of the operational aspect. Now let's take a quick look at the applications that run in the cloud. So here's, I can't go through all the applications, but I'll go through the 2 big ones, the storage and search. So this one's talking about storage. So this is an example of what we do for storage. This is, think about all your pictures, videos, they're all stored in the cloud, and this is what it runs on, in case it's running on Azure. So it's typically a distributed file system. So you can see that there are different layers. It's not a classic file system in the sense that you can do reads and writes to it and modify data. It's an append-only file system. So this helps a lot with ensuring that you're getting the most bandwidth out of the drives. You keep writing to this what we call extents, and you write up to 3 gigabytes, and then you seal it. Then you move on to the next 3 gigabyte chunk, and you keep doing that. If you end up having to modify data, you read the whole 3 gigabyte back, you modify the piece, and then write the 3 gigabyte thing back. So it's a very different way of doing file systems. And the reason you have to do that is because you want to get the most performance out of your streaming or write device. Taking a look at a different application, in this case it's search. This is the case of Bing, where you're doing internet search. So here it's a highly distributed application. You have rows and columns, where the rows are essentially used for load balancing, and the columns hold a piece of the internet. When a query comes in, it's distributed to all the columns, as you see on the left side, and then they all compute their local results and aggregate it and send it back up top. And then the aggregator will look at what is the best results that needs to be returned back to the user. Now, a key piece in that is a neural network, which is a way to do machine learning. The application is very unique in the sense that it's not only distributed at scale, but there are some parts of the application that don't necessarily run very well on a typical CPU. So that's where you get opportunities for maybe I can have some accelerators that I can put in the system for speeding up the query. And we'll talk more about that, but I just want to give you a sense of the types of applications. So, cloud workloads are very, very different from the classic workloads that we have had in enterprise for the past couple of decades. There are several opportunities for offloading computer-intensive tasks. CPUs end up doing a really good job for common functions, but there's a lot of new functions that are coming up where your CPU doesn't do the right amount of acceleration. So there you think about, okay, what can I use? Maybe I can use an accelerator for encryption, or maybe I can do FPGAs. There's a lot of opportunities there to offload the CPU-intensive tasks. The read patterns in some cases are read mostly write once. The example I just gave you for Bing, which is web search, just think about this, right? You have captured or crawled the internet, and you have queries coming in, and you want to return the result. You're just reading from the index. You're not doing any writes. So 24 hours a day, you're just reading, and once a day you write when you update the index. Very different workload. In the case of cloud storage, as I mentioned, it's sequential write streams. You try to avoid random writes because random writes are slow, and in case you have SSDs, they'll also start to have endurance issues. And as far as replication goes, there is no RAID. Nobody uses a RAID in the cloud. You end up doing synchronous replication or erasure coding of some kind. So workloads are very different, and the nature of the work. So essentially, when you end up talking about server design, it starts with what are you trying to solve for? What is the workload? And you can see that the workloads are so different. Operations model is so different, and the requirements for how this all comes together is so different. What does this server need to look like? So in addition to the design requirements, there's other requirements too, and I call it the Goldilocks problem. Just like not too hot, not too cold. You want to find a sweet spot in the middle. You want to make sure that you're hitting the right levels for performance, power, cost. You want this to be a design that can be deployed in an agile manner, so that supply chain guys, can not have to worry about capacity planning. You want to be able to do the right amount of customization so that you can extend functionality to new applications that are designed over the lifetime of the server. Sometimes the servers are in the data center for 3 years, and within that 3 years, there's new applications that will be created and deployed. So you want to make sure that the servers can be adapted for that over time. You want things to be simple because at the scale of 1 million servers, any bit of complexity is going to kill you. Simplicity always trumps complexity, and that You want things to be uniform so that when you start, aggregating all these applications, you can start to converge them into one common architecture. And you want to have a level of reliability, but the reliability here is more of a service level reliability, not necessarily hardware level. So these are other things that you have to take into account. And so again, talking about the architecture, so we're slowly getting into the design itself, right? So the architecture needs to be able to adapt to a variety of cloud workloads. Some examples are dense virtualization. This is what you see in a classic public cloud. You have virtual machines that are hosted in the cloud. You can rent a VM. You can host your own workload. Big data, you're doing MapReduce. You're doing, business intelligence. You're doing, some kind of IoT, sensor processing. Very different workload. High performance computing, bandwidth is king in that kind of workload and floating point. Mailbox, email hosting. Gaming, very latency sensitive. Media streaming, which is all about, hosting streams of video, and then, like YouTube, for example. So, but you want to have a common architecture though, and you can see that there are so many ways you can design this, but you want to still have a common architecture. Compute and on compute, storage, and networking, all these applications that I mentioned, they all have varying requirements. Some are very network heavy, some are very compute heavy, some are very storage heavy. So how do you balance that? And at the same time, you want to make sure that you have a general purpose design that can be used across all of these, but at the same time, you have some room for doing some specialization so that you can address those scenarios where you can do offloads. Secondly, you're deploying this across the globe. Europe, Asia, South America, US, and that brings up a challenge for what is the compatibility? There are different voltage standards, there are different safety and regulatory standards. How do you design, while you're designing an architecture that can meet the workloads, you can't ignore the fact that this has to go into different data center environments. It could be a data center that you build, it could be a data center that somebody else built, so you still want to have that flexibility. So let's take a look at this, right? So this gets us into the server design itself. So we contributed this server design to Open Compute last January, and you can find this all at the OCP website. But essentially, what you had there was, and I'll go into more details of the design itself. Essentially, there is a chassis, which is 12U. The mechanical CAD models for that are open source. The specifications for the whole design are open source. It's about 350 pages of documentation. The PCB blurber files are all there, and the source code for how you do systems management, so that your operations can be simplified, what I was talking about earlier, it's all there. The features of this design, so you have a 12U chassis with a lot of shared infrastructure. There is shared management, and the point about shared is so that you can amortize the cost of those components across a wider number of servers. So in this case, a chassis can hold 24 servers. And what we're trying to do here is how can you share a lot of the common components across these 24 servers so that the cost to each, the tax overhead, is minimized. So you see there is shared power. There are 6 power supplies in the back that deliver common 12-volt power. There is shared management. There is a chassis management card. And that removes a lot of the burden of the BMC, because the chassis manager becomes the front point for doing out-of-band access. There is a common shared signal backplane so that you can decouple the compute from the network, which is a key requirement, because network is evolving really fast. We have gone through 1 gig, 10 gig, and now 40 gig in the last 4 years. There are shared fans to help with cooling and thermal management. Again, and then the design itself, there's only 2 things here. There's a compute blade and there's a JBOD blade. That's it. And then you can figure out how you want to mix and match them. If you are doing a very compute-intensive application, you take this chassis and you populate the whole thing with compute blades, 24 compute blades. If you have an application that is doing storage, then you take maybe 1 compute blade and you can take multiple storage JBOD blades. And these are JBODs, they're not, so you can do an expansion. So you see that so all the challenges I mentioned before, the way we are solving it is by a very simple modular design, and there is a lot of shared componentry so that you can optimize the cost. It is ready for contract manufacturing, which means it's very cost optimized. It's very modular so that you can scale it up and down between storage and compute. Networking is something that I'll talk about in a second. But between storage and compute, you can scale it up and down by varying the number of compute blades versus storage blades. So that gives you that flexibility to match the workload that is deployed. Specific to some of the innovations we are driving, I want to call out a couple in this case. So there is an M.2 NVMe that we are introducing for the server. So for those of you who haven't seen an M.2, it's about this big. So think about a terabyte of SSD in a form factor this big. Unlike a 2.5-inch SSD, you can imagine that first of all it's PCI Express by 4, so you get better latency, higher bandwidth. Secondly, this is based on the same flash that is used in typical client devices. So what we're doing is we're bringing all the benefits of cost optimization from the client into the world of servers and into the same form factor that is being driven by volumes in the client. So this will help to drive the same economics in the server space for flash. And the other one, and I'll talk some more about that. There's some other things in addition to the form factor. There's some other things at the flash layer that are also different, which are unique to how the cloud operates. There is an FPGA card that we have built, and this goes for the specialization case that I mentioned. For the Bing example that I mentioned, if you recall, I was mentioning that there's a neural network that does machine learning. We have deployed FPGAs for that part of the application, and we are seeing up to 30% overall price performance benefit, which is huge. So talking about and by the way, if you go to the booth, you can see this, there is a sample there, so you can go and see it in person. So the design itself allows you to scale up and down. So I was talking about how you need to scale compute, storage, and networking to meet the different requirements of applications. Now you can go up to 28 cores in a half-U design. So depending on how intense your compute workload is, you can pick the right CPU. On the networking side, now it allows you to do 40 gigabit networking with routable RDMA. So again, you get a lot of flexibility on your network. You can go anywhere from 10 to 40. We talked about the M.2 flash up to 8 terabytes. So if you have an application that is very latency sensitive, you can introduce a bunch of flash in there. If the application is memory bound, such as in a database, you can go up to 512 gigabytes of memory, which is quite a bit. And of course, you can do accelerator card expansion. You can add a GPU, you can add FPGAs for specialized cases using the PCI Express by connector. And finally, for the data center integration, there is a 1600 watt power supply that is not only highly efficient, but it also is designed for load transfer considerations in the data center. There's a 20 millisecond hold up time in the power supply, so that when the power goes out, the utility, the load is still going to be seamless while it transitions over. So talking more about the SSD, so you see that the way the SSD requirements for the cloud are different. And that's been encapsulated in this design that we have. So essentially, I think the key point here is that data retention in the cloud is very different. So data retention is essentially a measure of, if I put data on a flash device, and if I unplug the flash device, how long does the data have to be there before I lose it? The JEDEC standard for MLC used to be 12 months, which is quite a long period. Imagine like unplugging a drive and putting it on a shelf for a year and coming back and expecting your data to be still there. Nobody does that in the cloud. At most, you will put it back in a few days, if at all. Most of the cases are where you use SSDs as a cache. So you unplug the thing, if the data goes away, it's fine because it's just a cache. So that big change that we made was start to require that data retention be less than a month. A month is still a long time, but you see that the curve for endurance starts to drop sharply after a month. So a month is a good number in that sense. And what that helps with is that you can get at least 2 times more endurance over whatever other techniques you're using for endurance. So if you're using LDPC codes and you went from, let's say 3K endurance to whatever 15K, you take the data retention down from 12 to 1 month, or 3 months to 1 month, and you get another boost in endurance. So which means more lifetime, which means more cost optimization for your product. So that's the uniqueness of how you can design a SSD that is cloud specific. And this is something that can be used in enterprise too, as long as you follow the same rules of caching and data retention for a month. The other one is the FPGA card. So this is what, in this case, we have an Altera FPGA that sits on a PCI by 8 interface. It's got 8 gigabytes of memory, and we connected this there is a paper on this that was published at ISCA earlier this year. So if you want to find out more details, you can go read that paper. But essentially, it connects in a 3D torus network, and it creates a pipeline where you can start to shard the data, and each FPGA works on a chunk of data and starts to, send it down the pipe. So, and the FPGA card is not, you can use it for any kind of application for that matter. You can use it for HPC, you can use it for machine learning. So that's how you extend the platform to do something custom for your workload. All in all, cloud workloads are very different, very diverse, and even though you want to have a common architecture, there is still a need for doing specialization. In this case, as I mentioned, I gave 2 examples. One was for Flash, where you did some specialization, and the other one was for FPGAs. There is that opportunity to do specialization, even though you want to have a common framework. The design for cloud scale computing, you may think that you just design for scale out and you're done, but in reality, you have to still be compatible with a lot of legacy infrastructure because you're deploying in third-party locations. You are co-hosting with some older gear. So it's not just this utopia of you can just design anything you want and deploy it. You have to take into account the legacy. And finally, now that we have OCP, there's a lot of momentum behind open compute, and open server designs offer a good way to drive a common standard in the industry on which you can build innovation and drive more extensibility, which can benefit the whole community at the same time because of the open nature of things. So that's something to think about as you look at new designs of how you can leverage open compute to extend the platforms that are in open compute, and at the same time create differentiation by creating extensibility. Thanks. I can take maybe one question.
We're actually, sorry, we're out of time. We're out of time. We're going to have to move on. But Kushagra, thanks very much, and please thank all our speakers.
Okay, thank you.
I encourage you to hunt them down. Kushagra's here. Dr. Lee went over there, I believe, and I lost track of Regine, but someone track her down. Thanks.